Okay, welcome back to bonding in part 4 of our series, which is actually video number 5. We're going to be talking about VSEPR, an acronym we hopefully will become quite familiar with. So VSEPR stands for Valence Shell Electron Pair Repulsion Theory, used to explain the shape of covalently bonded molecules. So essentially, the valence shell electron pairs are repulsed by each other. So they're trying to get as far away from each other as possible. So in your notes, we actually have a big giant chart, and I'm going to do these one per page. But on your chart for this video, we're only going to be filling out the first 4 columns on the left. We're not going to be looking at polarity or hybridization. Just Lewis structure, BP-LP, bond angle, and shape. So Lewis structure, that's something that we have covered significantly. Hopefully this is a good spot to start. HCl has 1 plus 7, which is 8 electrons. So it should look something like this. So there is my HCl. So now I need BP-LP. BP stands for bonding pair. This is the line between 2 atoms in a covalent bond. LP stands for lone pair. This is a pair of dots that's sitting by itself on an atom. Now, the trick is that this BP and LP both are talking about on the central atom. Bonding pairs and lone pairs on the central atom. Trick is, in our very first molecule, there is no central atom. Hydrogen's on the left, chlorine's on the right, nobody's in the middle. So for our BP-LP column, for our very first molecule, draw a giant X. It doesn't count. So now what we need is a bond angle and a shape. How are hydrogen and chlorine connected? Are they in a line, or maybe a squiggly line, or a circle, or some sort of triangular shape? Turns out it's a line. The shortest distance between 2 points is a straight line. So this bond angle, the angle between the hydrogen and the chlorine, is 180 degrees, and it's called, no surprise here, linear. So HCl is a linear molecule with a bond angle of 180 degrees. Let's look at BeCl2. Okay, Be is in group 2. It has 2 valence electrons. Chlorine is in group 17, so 2 times 7, 14 plus 2 is 16 electrons. Be in the center. Cl's on the outside. Give everybody an octet who needs one. Remember, Be doesn't need one. And there we go. There's our Lewis structure. We have 16 electrons in the picture. The picture's all good. Now, how does the Be and the Cl connect? First, we need bonding pairs and lone pairs. So this is bonding pairs and lone pairs on the central atom. Remember, the one in the center. So Be has 2 bonding pairs, one right there and one right there, which is a total of 2 bonding pairs. And it has no lone pairs. Like these dots over here, those are lone pairs, but those aren't on the center. So beryllium has 0. So this is a 2 and 0 here for bonding pairs and lone pairs. So in what shape are the Be and the Cl's connected? Is it a line? Is it an angle? It's a line! We've got another line with an angle of 180 degrees, also called linear. There's actually several different ways to make a linear molecule. One is with 2 atoms total, and the other is with 3 atoms total. So here's our BeCl2. All right, AlCl3. We have 3 electrons plus 3 times 7. 21 plus 3 is 24 electrons. Al in the center, Cl on the outside. Everybody an octet. 8, 16, 24 electrons. Okay, so there's our picture. As far as bonding pairs and lone pairs, on aluminum, there's 1, 2, 3 bonding pairs, 0 lone pairs because aluminum does not need an octet. It does not have any extra dots. Now the way we usually draw this kind of looks like a T, but valence shell electron pair repulsion means that the valence shell electron pairs want to get as far away from each other as possible. The chlorines want to get as far away from the other chlorines as they can. So if we put them in a T, then we've got angles of 90 degrees, and I think we can get them farther away than that. Ta-da! 120 degrees. We can get them 120 degrees apart. That's as far away as they can get. So now my valence shell electron pairs are repulsed by each other, and we've got a shape that's called trigonal planar. It is called trigonal planar because it's flat in one plane. It's a two-dimensional molecule rather than sticking out of the plane in 3D. Okay, next we have O3. That's 3 times 6, which is 18 electrons. That's an O with an O and an O. Recall that we have drawn this one already in our notes, and we ended up with something like that has 18 electrons. So we have a double bond on one side and a single bond on the other. Technically, it's a resonance between the two. So now we're going to count bonding pairs and lone pairs on the central atom. Oxygen has one lone pair of electrons, and for bonding pairs it has only two bonding pairs, not 3. This gets a little bit into hybridization. Remember that the first bond is the sigma bond, and the second bond is the pi bond. Well, the pi bond does not count as far as bonding pairs are concerned. We're actually only looking at the sigma bond. So really you can kind of think about this as the oxygen has 2 areas of electron density around it as far as bonding is concerned. 1, 2. 2 areas of electron density, that's 2 bonding pairs. And then another one down here for the lone pair. 2 bonding pairs, 1 lone pair. And since I messed up your picture, I'm going to draw it one more time for you, just so you'll have a pretty one. Well, pretty is a relative term, I suppose. So, what kind of shape is this going to make? It seems like it should be linear, because I've got an oxygen on the left and an oxygen on the right. But the problem is there is a pair of electrons that is a lone pair. And so this pair of electrons is a big giant ball of negative charge, a huge negative, and it's going to push these oxygens away from it as if it were an entire other atom. So those oxygens are not going to be 180 degrees apart. It's not going to be linear. In fact, this guy counts as my lone pair up here. It's pushing these a little bit less than 120 degrees apart from each other. It's not exactly trigonal like our AlCl3 was, but it's still pushing them almost 120 degrees away. This shape is called bent, because it was like a line, but it got bent. Technically, this one is bent planar because it is flat, two-dimensional in one plane. Later on, we'll see a bent non-planar, so I like to distinguish between the two. So, recap, giant lone pair pushes the bonding pairs away from each other and repels the bonding pairs more than the bonding pairs repel each other. It still has 3 areas of electron density, 1, 2, 3, so it has the basic shape of a trigonal planar, but because of the lone pair, the angle is actually a little bit less than you would expect. This angle is a little bit less than 120 degrees. Next we have CH4. Carbon has 4 valence electrons, plus the 4 for hydrogen is 8 total. Carbon's in the center. Hydrogens are around the outside. That's 2, 4, 6, 8. No lone pairs to deal with. That's just it. So, bonding pairs got 4, because carbon's bonded to 4 things. Lone pair got none. Carbon doesn't have any extra dots on it. So for shape, you would kind of think a square maybe, or a cross. It kind of looks like these guys are all 90 degrees apart from each other. But they're not. Because 3-dimensional space is available, we're actually going to take this hydrogen and pull it closer to us, kind of making it come out of the page, and this hydrogen and push it away from us, kind of going into the page, so that we'll end up with a shape that kind of looks like this. So this shape actually uses all three dimensions, pulls this one closer to you, pulls this one farther away, and causes every atom to be an equal 109.5 degrees apart from each other. The bonding angle is 109.5 degrees. And every one of them is 109.5 here, 109.5 there, 109.5 here, 109.5 there. Every single one of them becomes 109.5 apart because the valence shell electron pairs are trying to repel from each other and get as far away apart as possible. Okay, so as far as my shape name, this one kind of looks kind of right. You have a pyramid there. You end up with 4 sides, if you can see it. So kind of like a pyramid, kind of like that. And so then it's a 4-sided, and it's called tetrahedral. You can remember tetrahedral. The prefix tetra means 4. Just like in Tetris, your big score is when you get the 4 lines in a row. And here we've got 4 atoms. 1, 2, 3, 4. Tetrahedral. Next we have NH3. Nitrogen has 5 valence electrons plus 3 times 1 for hydrogen is 8 total. Nitrogen goes in the center. Hydrogen goes on the outside. That's 2, 4, 6, 7, 8. There's our Lewis structure. Bonding pairs, nitrogen has 3. Lone pairs, nitrogen has 1. This counts as a lone pair of electrons, not 2 individual, but 1 pair. So 3 bonding pairs, 1 lone pair. So what you should be seeing is 4 total areas of electron density around this nitrogen. 3 of them are hydrogens, bonding pairs, and 1 of them is a lone pair. So it's kind of going to look like your tetrahedral that you already had, except replace one of the hydrogens on the CH4 with a lone pair. That's going to repel the bonding pairs more than the bonding pairs repel each other. So we have the same basic tetrahedral shape, except that one of the things is a lone pair, which pushes these bonding pairs closer to each other, which causes the angle to be just slightly less than 109.5. It's actually not important to know whether it's 107 or 108.2, just that it's less than a normal tetrahedral should be because the lone pair repels the bonding pair more than the bonding pair repels each other. As far as a shape name, when you're naming the shape, you name it without the lone pair. Take the lone pair off and look at what you have left. And this should kind of look like a, hopefully, pyramid. And it's called pyramidal. Next we have water. That's 2 times the hydrogen plus the oxygen, 8 total electrons. Oxygen in the center, hydrogen's on the outside, 2, 4, 5, 6, 7, 8. There's my Lewis structure. Bonding pairs, oxygen has 2 because it's bonded to 2 hydrogens. Lone pairs, oxygen has 2 because there's 2 pairs of electrons on the oxygen. So you should be seeing 4 total areas of electron density here, which is a basic tetrahedral shape. But 2 of these areas are lone pairs, and these lone pairs are going to repel the bond pairs more than the bond pairs repel each other. Water is not a straight line, because those lone pairs are pushing on the hydrogens and getting the hydrogens closer together. Have this basic tetrahedral shape, but now 2 of our atoms have been replaced by lone pairs, and both of these guys make this giant ball of negative charge and push the hydrogens closer together so that this angle is even smaller than 109.5. It doesn't actually matter whether it's 107 or 104, just smaller than 109.5. So now, when we're naming it without the lone pairs. We're just looking at the shape without the lone pairs for the name. And this looks very much like the bent planar that we had before. But this time the bent is not planar because the lone pairs are actually not in the same plane. It's not flat two-dimensional. So this is bent non-planar. And I like to distinguish between the two of them. Bent planar has one lone pair, bent non-planar has two lone pairs. Bent planar is flat two-dimensional, bent non-planar is 3D. All right, now we're getting into the expanded octets. PCl5, there's going to be 5 chlorines around the phosphorus. 5 plus 5 times 7, 35 plus 5 is 40 electrons. So PCl5. And that's 40 electrons. So there's my PCl5. That's my beautiful structure. Now, we want to get, bonding pairs and lone pairs. Phosphorus has 5 bonding pairs because phosphorus is connected to 5 chlorines. Phosphorus has no lone pairs because there's no extra dots on the phosphorus itself. I don't care about the chlorines, I'm just looking at the central atom. So as far as the shape is concerned, it seems like this would be some sort of pentagon, but you're thinking in two-dimensional space. This is not two-dimensional, it's actually three-dimensional. Ooh, that kind of looks like a sand dollar. And it's totally wrong, because we have 3D here, not just 2D. So what we're going to end up having is 3 of these guys are going to be coming out planar in the middle of it. And then another 2 of these guys are going to be coming off the top and the bottom. Let me show you what I mean. 5 things around the center, 3 of them kind of make a trigonal shape, and the other 2 kind of make a linear shape. So the bond angle here between these are 90 degrees, and the bond angle here between those guys are 120 degrees. We're not interested in the larger bond angle of 180. We're looking at between the closest atoms. So our bond angle is actually 2 different bond angles, 90 and 120. As far as the shape is concerned, there should be a triangle here and in the back. Do you see that? Kind of looks like a pyramid. But then there's also a triangle here and, let's see, here and in the back, which kind of also looks like a pyramid. Let's see if I can draw a pyramid. This is a bad pyramid. So it kind of looks like 2 pyramids on top of each other. So it's got a trigonal in the middle, but then there's 2 pyramids. So it's called trigonal bipyramidal. Trigonal with 2 pyramids attached. SF4. Okay. 6 plus 4 times 7. That is 28 plus 6, so 34 electrons. Sulfur with 4 fluorines. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Uh-oh, need 34 electrons, not 32. So my extra pair is going in the center. This is an expanded octet. Okay, so that means sulfur has 4 bonding pairs because of the 4 fluorines that it's attached to, but also 1 lone pair. So as far as areas of electron density, we have the fluorine times 4 fluorines, but then also this lone pair. So it's got 5 total areas of where the electrons can be. And remember this one, even though it looks like a tiny, teeny pair, really it's a huge ball of negative charge. And it's pushing those fluorines away from each other. So what shape does that mean? Well, it's got the basic shape of the trigonal bipyramidal. This is the exact same thing as our trigonal bipyramidal was before, except that one of the parts on the trigonal is a lone pair. Instead of an atom, it's replaced by a lone pair. And remember, this lone pair, this huge ball of negative charge, is pushing all the other atoms closer together. So my angle now is going to be less than 90. And between these 2 less than 120. It doesn't have to be exact numbers, just less than 90, less than 120, because big ball of negative charge is pushing them closer to each other. So as far as a shape is concerned, now what are we going to call this shape? If I take off those little numbers, what does it kind of look like? Let me draw those things back in. Well, here, what if you imagine there's a person sitting right there and another person sitting right there, and both of these people are very happy because they're on a seesaw. It's a seesaw. Doesn't it look like a seesaw? That's the actual technical name for it. Not kidding. Okay, BRF3. 7 plus 3 times 7, that's 28 electrons. BR, F, 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 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Needs some more. 26, 28. That's 2 extra lone pairs on the bromine. So there's 3 total bonding pairs on the bromine and 2 total lone pairs on the bromine. 5 total areas of electron density. So we've got the 3 fluorines plus the 2 lone pairs. Maybe you're seeing in this shape a little trigonal bipyramidal, except that in this new trigonal bipyramidal, 2 of my atoms have been replaced by lone pairs. But these lone pairs are kind of symmetrical, which gives this angle right at 90 degrees, or maybe a little bit less than 90 degrees. All right, so as far as what the shape is called, take off the lone pairs and see what you have left. You've got that linear with the line. Hey, doesn't that look like a capital T? This one's called T-shape. Seriously, because it looks like a T. Next, I3 minus. Okay, so this is 3 times 7 plus 1 more. The minus sign means we're gaining an electron. So this is going to end up being 22 electrons total. I, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. That is 3 lone pairs on the iodine. So 2 bonding pairs, 3 lone pairs, 5 total areas of electron density around the center, 2 of them bonding pairs, 3 of them lone pairs. So we have that basic trigonal bipyramidal shape, except that now 3 of our atoms have been replaced by lone pairs. These are definitely symmetrical lone pairs, so even though this is a giant ball of negative charge, it's not affecting the angle of the other 2. So the angle of the other 2 is 180 degrees, just like it looks. And this is another example of linear. So we've seen 3 examples of linear so far. One with 2 atoms total, 3 atoms, 2 bonding pairs, no lone pairs. And here's another 3 atoms, 2 bonding pairs, 3 lone pairs. All of them are plain linear. Okay, let's look at the next one. Now we're going to have 6 things around the central atom. Sulfur has 6 plus 6 fluorines times 7. So 6 times 7 is 42, plus another 6 is 48. Okay, sulfur with 6 fluorines around it. Make sure you leave enough room for all those dots. Dots and dots and dots. More dots than you could ever care to draw. 48 electrons. So this is totally fine. Sulfur has, let's try that again. Sulfur has 6 bonding pairs, and there's no lone pairs on the central atom. It has 6 things around it. This is not a hexagon. This is instead using all 3 dimensions of space as much as we can. So it kind of looks like these 4 guys are going to form a square around the center, and then these 2 guys are going to go up and down in a linear-ish fashion. That's exactly what we have. the two up and down kind of linear, and these four guys are kind of going to form a square. And notice that this can be rotated at any angle. It will look exactly the same no matter what angle it is. And so the angle between the two atoms is 90 degrees. Between any two atoms is 90 degrees. No matter which any two atoms you pick. All of the angles around the entire molecule are all 90 degrees. So, what is this shape called? Well, if you think about it the same way we thought about the tetrahedral, there's a plane right here, and another one there, another one there, and another one in the back. That kind of makes a square pyramid. And on the bottom we have a plane right there, and another one here, and another one there, and another one there. Kind of looks like another pyramid. So again, we have two pyramids on top of each other, each triangular pyramids. Oh, that's not a very good picture, but just pretend. So the takeaway is that there are 8 sides to the pyramid. It is not square bipyramidal. It is not square bipyramidal. It is not square bipyramidal. It is instead octahedral, because there are 8 faces to these pyramids. Okay, then we have BRF5. That'll be 7 plus 5 times 7, which is really 6 times 7, which is 42 electrons. BR with 5 Fs. 1, 2, 3, 4, 5. Everybody gets an octet. 8, 16, 24, 32, 40, an extra lone pair on the bromine. So bromine has 5 bonding pairs and 1 lone pair. Hopefully you're thinking this is 6 things around the center, just like SF6. So it's going to have the same basic shape as SF6, just pick one of those and replace it with a lone pair. The same basic octahedral shape, just pick one of them and replace it with a lone pair. Big giant ball of negative charge is going to push everybody closer together, so my bond angle is going to be just a little bit less than 90 degrees. Doesn't really matter how much less, just a little bit less, because the giant ball of negative charge is repelling. Valence shell electron pair repulsion. So now my shape. Do you see a square here? And if you bring all the sides of that square up to the center, do you see a pyramid? This one is square pyramidal. When you put the one on the bottom, it becomes octahedral, but if you only have one pyramid, it is square pyramidal. All right, we're on to the very last one. XEF4. That'll be 8 plus 4 times 7. 28 and 8 is 36 electrons. XE with 4 F's around it. 8, 16, 24, 32, 33, 34, 35, 36. A lone pair here, a lone pair there. So XE is going to end up with 4 bonding pairs and 2 lone pairs. 4 bonding pairs, 2 lone pairs. Hopefully you're seeing that there's still 6 areas of electron density around the atom. 4 of them are atoms, 2 of them are lone pairs. So let's see what that does to the shape. Using 2 of the things in my octahedral with lone pairs. There's one here and there's one there. When we replace those 2 things with octahedral, they kind of have symmetry. And so this one on the bottom is pushing the guys away from it. But this one on the top is doing the exact same thing. So they're pushing with equal speed because they're both the same lone pairs. So my final shape has angles of exactly 90 degrees, not less than, because the lone pair on the top and the lone pair on the bottom are pulling or pushing the same amount. So for my shape, this kind of looks like a cross. But instead of thinking of it as a cross, let's connect them a different way. and make it look like a square. Square planar, to be exact, because it's flat in a two-dimensional plane. So here we have square planar, which is the very last shape that you need to know for the AP test, and that is all your shapes. We'll see you next time.